doesn't, does it? Okay. So the common logarithm is the log base 10 of whatever x is, okay? Log base 10, but we don't really write the 10. It's just understood 10. So we call it common log. Now, it's the inverse of y equals 2 to the x, or any kind of exponent, okay? So these, now when y is e to the x, remember e is a number, it's an irrational number like pi. So when e is the base, it becomes the natural log, and it looks like this, natural log of x, okay? And so natural log, when you see ln, that means the base is e now instead of the number 10, okay? Instead of the number 10. E is a number, your calculator is aware of the number. Now when you graph it, it's going to look a lot the same. That asymptote is not changing. It's still where x is equal to 0. And that key point is still at 1, 0. So it looks almost identical to the logarithm graph, all right? It's slightly different with the different base, but it doesn't make a difference in how things are looking. All right, so all we have to do is consider the properties. Now, if you know these properties, it makes solving really easy, but you got to get used to the properties. So today's job is to get used to the properties and changing the graphs up a little bit. Okay, so the natural log of 1 is equal to 0. Well, why is that? Because the base is e, right? To get rid of the logarithm, I swirl it out. So I would say e to the 0 equals 1. Anything to the 0 power is 1, right? Look at number 2. If I swirl this one, it's saying e to the first power is equal to e. And you're like, well, duh. Yes, it is, of course. But that's what this property is telling us in natural log mode, basically. Number 3, the natural log of e to the x is equal to x. Because if I swirled it, you would see e to the x is equal to e to the x. Looks identical, they are the same. All of this was in your notes in your video, so I'm not going to spend too much more time doing it because you should have already done it. But just going to show you a few of these because this is how you use those properties to solve. Okay? So, for instance, look at number 4. What did we say up there in the properties that the natural log of e was equal to? Look at the property, the natural log properties up here. Natural log of e, what was that equal to up there? It's 1, right? So I can rewrite this as 2 times 1, and that's just a 2. Because of this property right here. Right? That's where you got to know those properties. It makes it so much easier. Okay, let's try, what about number 8? What would you say on number 8? E to the natural log of 7 is, look at your properties. Which one does it look like? 1, 2, 3, or 4?
3.
Looks like 3. Mm-hmm. Yep, we're using property number 3 right here. I can deduce that this is just a 7. E to the natural log cancels one another out. And what about number 6? 5 times the natural log of 1. So natural log of 1 is what? Look at your properties. It's just 0, right? Property number 1, do you see that? So all I have to do is do 5 times 0, and I don't need a calculator. That one's just 0. Right? So your goal is to not use your calculator on these because you got to know these properties. Now, let me go back down here and do some graphing with you just to remind you how to do these graphs, because this is where people mess up the most on this test coming up, is the graphing. So we're going to do a lot of practice with graphing. But here we go. Natural log of negative x. What is that negative in the parenthesis going to do to my graph? Reflect it over y. All right. Now, that asymptote's going to stay put where x is equal to 0. That's not changing. Okay, and my parent function, I'm just going to put it right here just in dotted lines because this is where it starts, right? But if it reflects over y, that means it's going this direction. And now, this point that was at 1, 0 is now at negative 1, 0. And it's getting reflected to the left. Okay? Asymptote didn't change, it just got reflected. So what can you tell me about the domain of this function? You just said these on your project. Yeah. Domain?
Negative infinity 0.
Good. Negative infinity to 0. Okay, what kind of ending do I put on 0? A parenthesis or a bracket? Why is it a parenthesis? It's an asymptote. It never actually reaches that, right? But it approaches it, okay? Vertical asymptote would be at x equals 0. You always have to have x equals on there. If you don't, you're going to miss points. X-intercept, where is it touching the x-axis? Well, negative 1, 0. Okay? So look at the next one. Natural log of x minus 1. What is the x minus 1 in parentheses telling us? Yeah, it's going to move the whole thing right 1. Starting with the asymptote. So my asymptote that was at 0 now is where x is equal to 1. And notice there's always going to be this 1 unit gap between the asymptote and the intercept. Okay? So if my asymptote is at 1, that means my next point is at 2. Because it's not moving up or down, it's going to stay on that x-axis. So we're doing this. So then my domain would be 0 to positive infinity. Okay? Actually, it's not 0. It's 1, isn't it? Because my asymptote moved. It's 1. And my x-intercept is now at 2, 0. Okay? Just like before, notice the pattern here. Whatever your asymptote is the end of your domain. One of the ends, right? Asymptote 0, and there's one of my ends. So use that as a guideline. So 4.2c is the rest of 4.2. It should be like number 30 through 45, something like that. A big chunk of them are just like these right in here, where you're using those properties. So have those properties side by side so you can just reference them and knock them out pretty quick. They're meant to make them easier, all right? Get really used to those because as we move into finding or solving equations, you're going to need those properties to simplify your life, all right? And then you have some graphing stuff. Some of them you're actually going to graph, and some of them you're just going to look at the equation and tell me what changed, okay? So